and welcome to our review and introduction of some of our terminology in our solutions unit. A solution is a homogeneous mixture of a solute dissolved in a solvent. For our particular purposes, this is when we talk about aqueous solutions dissolved in water. So the solvent is the dissolving medium, typically a liquid, often water, especially in Regents chemistry. Our solute is what is getting dissolved, which is usually a solid. So if you're talking about salt water, for example, so you might see something written like this. This right here is our solute, our solid salt. This AQ right here tells us we are dissolving in water as our solvent. So just a little terminology thing for you here in the Regents chemistry world. Again, AQ, we've talked about this ding, ding, ding idea a few times. We're going to be dealing really in this primarily with aqueous solutions in this unit, which is a solution where water is your solvent. Properties of solutions is that they are essentially clear, meaning that you do not actually see the particles in them. They have very small particle size. The only time a solution actually looks a whole lot different than water is when you have like a transition metal, like a copper compound solution, because those are colored or blue. And some things that don't dissolve as well, sometimes you get to see a little fogginess in there if you have something that's not quite so soluble. However, in a true solution, the solid should not be visible and should not settle out when the solution stands. It will pass through filter paper without being separated. So you can try to filter salt water, but because the water molecules and the salt ions are so similar in size, they cannot be separated. I really like this visual here. It shows if you compare a suspension, which is, when you have really large visible particles, that'd be something like salad dressing or soup, versus a colloid we talked about earlier in the year, which would be something like milk. So those particles, you need a microphone or a microscope to see, versus a true solution, you have very, very small particle size, and the particles are so similar in size to water that filtration does not allow them to be separated. This is not in your notes. You don't need to take notes on this. This is something we talked about earlier in the year. So I just want to mention these terms again so you're familiar with them. So solutions are homogeneous mixtures. Here are a couple heterogeneous mixtures. Colloids with particles that are really small, so they don't settle out, and you can actually see them with a microscope, but not our eyes. Milk is an example of a colloid. Milk is actually, even though it looks homogenized by the processes before we buy it, it is actually heterogeneous. A suspension, coffee grinds in water, something like that, those particles will settle out. And they're much larger and visible to the naked eye. So those are both examples of heterogeneous mixtures. The Tyndall effect, again, is something that is going to happen due to light scattering by suspended particles. This is not going to happen in solutions because the particles in solutions are so small that they don't block any of the light trying to pass through the mixture. So electrolytes in solution. Remember, in a definition of electrolyte is something that will conduct an electric current when dissolved in water. A solution that has electrolytes in it has mobile charged particles. We talked about this in the last unit. In order to conduct electricity, you need mobile charged particles. So our mobile charged particles, our mobile charged particles in this case are going to be ions in solution. So things that are going to be electrolytes in solution are going to be ionic compounds, which will give us mobile ions when they're dissolved in water. Non-electrolytes are things that dissolve but do not give charged particles. Where we saw this before in terms of demos, salt versus sugar. So the sugar did not dissolve in water, or I'm sorry, the sugar did dissolve in water, but did not actually conduct an electric current, whereas salt, when it dissolves in water, will conduct an electric current. An important note, remember, solutions are homogeneous mixtures, not substances. They're a mixture because you always have water there with something else, so that is two separate things. Now, the reason that we can have something be an electrolyte is because of how ionic compounds dissolve. They do so by something called dissociation. Dissociation is basically breaking apart. So again, when we see something written like with an AQ, that's telling us that our solvent is water, and in this case that our solute is sodium chloride or salt. So why does this act like it's an electrolyte in an aqueous solution? The salt itself, when it's put into water, will break apart or dissociate into these two ions, which I've kind of shown in that beaker right there. So then you end up with these charged particles that are floating around. So in an aqueous solution, we have a situation where we now have mobile charged particles that can move around and conduct an electric current. So water dissolves ionic compounds because there are charges that can interact. So we have talked about the polarity of water, the fact that up near oxygen, it's a little bit negative, and down near hydrogen, it's a little bit positive. So what allows ionic compounds to actually dissociate in solution is the fact that when a water molecule approaches an ion, it has an reaction. So a positive ion, like a sodium, will interact with the oxygen side of a water molecule. And that water molecule wants to float around and pull that positive ion with it. The hydrogen side can react with negative ions to do the same thing. They can actually completely surround them and essentially, float around carrying them in solution, which is what we call solvation. To give you a little bit more of a visual of this, so if you start with your NaCl stuck together, those polar water molecules are coming up and interacting. You can see in the first diagram, this negative charge side of water is interacting with the sodium. Positive charge side is acting with the chlorine. Water will overcome the attractive forces within that crystal and pull the sodium and the chlorine apart from one another. So a Regents term to know is dissociation, which means ions breaking apart in solution. And essentially the polarity of water is responsible for this. So you can kind of just visualize these water molecules. They're able to float up. They're able to kind of interact with one another and essentially float away together. Same thing's going to happen right here. They're going to float now. Oops. Sorry, control those two fingers. Sorry. They're going to be able to float away together. I am terrible at making animations, but luckily not everybody is. So, I have a nice animation for you right here. So in this animation, what we're going to see is we are going to shake some salt into a beaker. So we're shaking just regular old NaCl into this beaker. We're going to zoom into the molecular level after we stir this around a little bit. So as we zoom into the molecular level, what we're seeing now is that crystal with the positive Nas and the negative Cls, and the water molecules are pulling them away. So it really does actually take a few water molecules to pull each of these ions off of the crystal. Now those ions can move around in solution, which allows them to be mobile charged particles and conduct an electric current. So it's very important to notice when you're looking at this animation that the positively charged hydrogens face the green negative chlorines, and that those negatively charged oxygens are facing your positively charged sodium atoms. Sodium ions, I should say, sorry.